In this video, we're going to take a look at phase changes. In particular, we're going to look at the energy associated with phase changes, and we're going to look at ways of charting phase changes. So we saw in previous exercises that one factor that impacted phase at a particular temperature is the strength of that substance's intermolecular forces. So how strongly attracted the particles are to one another governs the phase. We also know from our everyday experiences that matter can change phases. These phase changes are the result of a change in temperature or pressure. Increasing temperature increases the energy, which gives the particles a better ability to break attractions. Temperature is changed through the transfer of heat, either into or out of the substance. So the phase we are at a particular temperature is governed by how strong our attractions are, and what temperature we need to get our substance to in order to get that phase change to occur depends on how strong those attractions are. So stronger attractions, more energy, higher temperatures. So recall from our first semester chemistry that heat transfer is referred to as enthalpy. We represent that with a delta H. That's the change in enthalpy, or the change in heat. As particles gain energy, they also gain disorder as they move more and spread out more. That change in disorder is referred to as entropy. With every phase change, there is associated enthalpy and entropy. So for example, we're all familiar with ice melting. Ice melts as a result of solid water absorbing heat. So if we're absorbing heat, we have a positive delta H. As it does so, that absorbed energy begins to break attractions, which allows the particles to move more, becoming more disordered as they enter the liquid phase. Positive delta S. This phase change will occur above certain temperatures. That is, spontaneity is temperature dependent. Recall that when enthalpy and entropy are both positive, this process described as being entropy driven. It is the gain of entropy that leads to the change occurring despite the increased energy. So we're going to walk through different phase changes, but before we do so, let's review again a little bit about enthalpy and entropy. So we said enthalpy that is the transfer of heat. We're going to call that delta H. So if something gains heat, so it's a positive delta H, that means heat is absorbed. And recall, if heat is absorbed, we describe that as being endothermic. If we have a negative delta H, that means heat is released or decreased or removed. And it's exothermic. And then we also have, as part of thermodynamics, we have entropy. Entropy is the degree of randomness or disorder. It is a form of energy. We're going to look at the change in disorder, delta S. If delta S is positive, that means that my particles become more random or more disordered. If delta S is negative, they are more ordered. So if we look at some phase changes, so we can go from solid to liquid to gas. So your worksheet only looks at some specific phase changes. We're going to go ahead and look at all of them. So solid, liquid, gas. As we go from solid to a liquid, so again, this is something you're familiar with. You know that if you want to melt ice, you've got to heat it. Take an ice cube, you want it to melt, you're going to leave it out, Just simply leave it out on the counter, it's going to melt. So going from a solid to a liquid, that requires that we supply energy. So we have to absorb energy. So that means we're going to have a positive delta H. So we add energy. Remember, we're doing so to break our intermolecular forces. So we're adding energy to break attractions. Now, as those attractions break, particles begin to move more. And if particles are moving more, they're going to become more disordered or more random. So that means as we're supplying heat to my solid and my forces start to break and my particles start to move more, we're going to gain entropy. So we have a positive delta S. Now, as we go from a liquid to a gas, so we know if we want to evaporate water, again, we can heat it. So if we're heating that water to evaporate it, heat's being absorbed. We've got a positive delta H. Again, going from a liquid to a gas, we start to break all of our intermolecular forces. As we break all those attractions, particles can now move freely. And as they move more freely, they're going to be more random. So we have a positive delta S. Now, the signs of delta H and delta S determine if a process is spontaneous. So you may recall something called Gibbs free energy, delta G. That's your overall energy change. For a process to be spontaneous, we have to have an overall delta G that's negative. And we can get that a couple of ways. Something is going to be 100% spontaneous. When our delta H is negative and delta S is positive. So that means it always occurs. Doesn't matter the temperature, as long as we have that release of heat, releasing heat, going to a lower energy state is always more stable. Delta S being positive, so being more disordered is a more stable state. That'll be 100% spontaneous. Something is 100% non-spontaneous when delta H is positive and delta S is negative. So we are supplying heat to force something into a more ordered state. That's not happening. It's not energetically favorable. But these are cases where the signs are opposites. When delta H is positive and delta S is positive, or when delta H is negative and delta S is negative, it's going to depend on temperature. So we're going to have a temperature at which our spontaneity changes. And so in the case of phase changes, so delta H and delta S's are positive if we're going in that forward direction, solid to liquid to gas. Or same would be true if we looked at sublimation. So we went from solid to gas. So solid to liquid, we've got melting. Liquid to gas, we've got vaporization. Solid to gas, we would have sublimation. These are all going to be temperature dependent. So we know that ice does not always spontaneously melt. If I leave that ice in my freezer, it's going to stay ice. It's not going to spontaneously melt. So it requires a certain threshold temperature. If I leave that ice out on the counter, I don't have to do anything else. At that temperature, because it's higher than the threshold, it's going to melt. If I continue to leave it there, eventually it's going to evaporate. Now remember that our phase changes can go the other direction as well. So we could go from a gas to a liquid, so we could have condensation occur. we could go from a liquid to a solid. So we'd have freezing. So if I'm going from a gas to a liquid, we have to take random particles that are moving freely, and we've got to get them now stuck together. To do that, we've got to slow our particles down. We've got to take energy away. And so we are going to remove, we're going to cool our sample down. When we cool a sample down, we are removing heat, we are removing energy. So we get a negative delta H. So we remove energy. As we remove that energy, my particles slow down. And they're going to begin to stick. And because we've removed that energy, those particles don't have enough energy to break attractions. So they remain stuck. And so that's how we're going to go from that gas to that liquid phase. We're going to remove enough energy that particles begin to stick, but we still have some energy to break some attractions, so we have some motion. But as particles begin to stick, they're no longer moving around freely. They're going to become more ordered. And if they're becoming more ordered, we have a negative delta S. Same is true going from a liquid to solid. We've got to cool that sample down even further, so we're removing more energy. We have even less energy to break attractions, so particles stick together more, becoming that rigid structure of the solid, which is much more ordered, so we have a negative delta S. Same is true going from a gas to a solid, which is deposition. We're going to have negative delta H and negative delta S. And so again, these are going to be spontaneous processes. They'll occur on their own, but they will do so at particular temperatures. Now we can chart phase changes using two types of diagrams. We can use a heating/cooling curve or a phase diagram. So first we'll take a look at heating and cooling curves. These curves are going to track the changes in temperature as either heat is added in the case of a heating curve or heat is removed in the case of a cooling curve. These types of curves are particularly useful in identifying melting and boiling points of an unknown substance. You're going to get to do this in lab. You're going to have a substance, you'll know what that substance is, but you're going to have a substance who you're going to create a cooling curve for, and you're going to use it to identify the freezing point of that substance. So here in our image, we have got the heating curve for water. And we're going to notice from one heating curve to the next, we've got several features. We're going to see these rises, and then we're going to see these plateaus. So in the case of water, we know that water freezes at 0. So if we're below that freezing point, so here we're starting at negative 25 degrees Celsius to 0. What we're going to do, so we start at negative 25, we're going to add heat, and we're going to see how the temperature changes. From negative 25 to 0, we're before the melting point. During that time, we're seeing solid ice. Our diagram is indicating that as heat is added, the temperature is rising until we reach that melting point of 0 Celsius. Then, when we're at 0, we see this plateau. During this time, added heat does not change the temperature. The reason for this is that that heat is actually being used during that time to break attractions. And we end up starting to get a mixture, so it's not instantaneous. We're going to get this mixture of solid and liquid until enough heat is added to enter the liquid state. You guys have seen phases change. Got ice, you know it's not ice 1 second and all of a sudden liquid the next. It takes time. You start to see that ice slowly melt. So if you left ice on the counter over time, you'd start to see a puddle slowly form and you get a mixture of ice and liquid for a period of time. Now, we continue to add heat, and it's going to remain at that plateau until we reach enough heat to break our forces and enter the next phase. So that's what we're seeing here. We've got this plateau, we've added heat, we're still at 0 Celsius, the temperature hasn't changed. Once we've added enough heat to break our attractions, we're going to see that temperature rise again. And so from 0 to 100 here. So for water, remember, the boiling point is 100 degrees Celsius. So after the melting point, we see the temperature rise again until the boiling point is reached. Once we reach that boiling point, again, we see this plateau. When we're at the boiling point, at 100, again, the temperature is not rising because that added heat is being used to break attractions. We're breaking all the liquid phase attractions so that we can enter the gas phase. We get a mixture of liquid and gas present until we've gained enough energy to break all of the attractions and we can enter that gas phase. Notice that melting points, or not just notice, but melting points and boiling points can be found experimentally through charts just like this. We're going to chart the temperature changes over time, and we locate the intersections of the plateaus. So notice again, we've got this plateau and this rise. Where they intersect is my melting point. Here, where this plateau and this rise intersects, that is going to be my vaporization point. So, we looked at an example of a heating curve. The difference between a heating curve and a cooling curve is going to be that with the heating curve, we chart temperature as we add heat. The cooling curve, we're going to remove heat. So we're going to look at temperature as it cools down. It's going to look the exact opposite. So it's going to be the opposite of the heating curve. So instead of starting at a low temperature, we would start at a high temperature. Let's see our plateau as we remove heat. Drop until we reach 0. Then we see our plateau again, and so on. So it's just the opposite. We're going to find our melting points, or we're going to find our different points the same way. So where these meet, this is where condensation occurs. If we're cooling, where these meet, this is where freezing occurs. Again, if we're cooling. So in terms of heating curves and cooling curves, and they tell us more information too. We could actually use the slopes of these curves to get information about the energy, about the heat, so our delta H. We're not going to get into that in this course, but that can be done. What we want to be able to do is use these curves to identify where we're going to see certain phases and phase changes. We want to identify our melting points and boiling points. So looking at this heating curve, we're asked for the melting point of this substance. So my melting point is going to be here. This is where we go from solid, we start to enter the liquid phase at 50 degrees Celsius. Now, this is a heating curve, but if we were cooling this, if we were going from the liquid to the solid, the point at which we start to go from liquid to the solid is our freezing point. Notice these are the same temperature. So the melting point and freezing point of water is 0 Celsius. Which direction we go in depends on if we are adding or removing heat. So if we're adding heat, we're going to melt. If we are removing heat, we're going to freeze. Now we're asked to label this graph with solid, liquid, or gas. So at low temperatures, we start out solid. We reach our plateau, we're going to see a mixture of solid and liquid. Once we've completely melted, we're going to have our liquid. We're going to see that temperature rise till we get to our next plateau where we're going to see a mixture of liquid and gas. And then once we have broken all of our attractions, we're just going to see gas. So where we've got that mixture of solid and liquid, this is where our melting is occurring. Where we have the liquid and the gas, this is where our vaporization is occurring.